that there.
Hello, Jim.
Good morning.
Hey, thanks for chiming in.
Yes, just curious to take a look at what you got here.
Awesome.
Our other presenters will be joining shortly. Fortunately, I kicked this off because we had two seminars back to back, and so they're just wrapping up the first one with a lot of Q&A, and they'll be joining shortly. So I'm happy to wait a few more minutes. I'll wait for your signal, Jeff, or anyone else to let me know when to get started. No issues if we need to wait a few more minutes.
Sure. Good morning, Jerry.
Morning.
It's been a short few years, I think, since we last talked.
Yeah, it has.
Jerry's with Insulet, Fred.
Oh, okay, great.
Thanks for joining.
Sure.
Yeah, in my prior life, I worked with Insulet. So I'd worked for Renaissance. So I know TJ Nivio and a lot of Hans, etc. So I've had some workings with them.
Oh, cool.
Yeah. So how are things up in the greater Boston area? I hear the Scottish Tartan Army have taken over, right? You guys are almost out of beer. I mean, I've seen some of the videos. They just look like so much fun in Fenway. I'm like, wow. I was like, I felt like driving up there. It was only 3.5 hours. It just looks like they're such a joyous and festive environment.
Yeah, I only watched the U.S. game, or the first game, but I haven't been out with the crowds.
Yeah, I read somewhere they said if the U.S. finishes first in their group and England finishes second, and we both win our round of 16, that we would meet up on July 4th in Philadelphia, USA versus England, the 250th anniversary. I mean, that would a lot has to happen for that to occur, but that would be kind of cool.
That is cool.
Yeah, it would be. Fred, we definitely had a few others, right? Okay. Here's Richard Boo.
All right. Great. Well, I can certainly kick things off. Again, the first few slides are just introductory in nature, and the meat of it doesn't start until a few minutes in. So if there's some late arrivers, that's completely fine. So, okay, with that.
Good morning, Richard.
Let me share my screen. All right. Oh, let me just do this, put it in full screen mode. Can everyone see my screen?
Yes.
Yes, sir.
Great. Excellent. Well, thank you very much for the opportunity and welcome to the NanoPower Virtual Seminar Series. So we're kicking off this series this week, and what I'll do is I'll talk a little bit about the history of NanoPower, then we'll dive into to some of the details. So today's agenda, I'm going to introduce you to the presenters. We'll talk a little bit about an introduction to NanoPower and the nPZero ecosystem, discuss a little bit about the recent awards we've won in the industry and some of the recognition we received. We'll show you some real use cases, right? Some real examples where customers have built some hardware and able to dramatically show significant reductions in power consumption. And then we'll transition over to Torben. He'll go into some detail about accelerating your next design and some of the tools that we have to make that available. So we'd like to have this be an interactive session. If you have questions, by all means, please just interrupt any of the presenters or put the question in the chat and we'll be happy to get to them. So first, the NanoPower team. My name is Fred Buonaiuto. I'm the Director of Sales for the Americas. I'm located in Northern New Jersey. Anthony Carter is on the line as well. He's the VP of Worldwide Sales based in the UK. And Torben is on as well. Torben is based in Norway. He is our Customer Success Manager, here to help customers, provide with him and his team, providing technical support, helping you to get your designs up and running. And so our contact information is here. In addition, you'll see just below Torben's email address is the technical support line. So you can use that to enter in any type of request, and it will get routed to Torben and his team. So we're pleased to have this seminar along with our partner Selmark in the New England market, and really thrilled to introduce you to NanoPower. So who is NanoPower? We like to say we essentially are a new solution to an old problem, right? And what is that old problem? Well, it's battery life, right? It's a constant problem. And what we've done at NanoPower is really have defined what we're calling a new category of IC that can dramatically reduce power consumption. We're calling it a power saving IC. And so who is NanoPower? Many of you probably are just recently hearing about NanoPower. And so you're thinking, oh, this is a pretty new company, but the reality is we've been in existence since 2017. We're a European fabless IC company with operations in Norway and Portugal. Our design team is based in Portugal, and really pioneers in sub-threshold design. And the nPZero, what it is it's basically a power-saving companion IC. So that new category. And what it does is essentially it doesn't replace any device, but it eliminates unnecessary NCU runtime. And it can in general, what it does is, if implemented properly, can help to reduce power consumption during long idle and sleep periods. And finally, Torben is also going to discuss a little bit about our ecosystem and the dev portal, and essentially all the tools that we've made available to engineers without registering. They're just free on our dev portal to allow faster time to market and reducing those design cycles. So, Anthony, if you'd like to take this slide, talking a little bit about some of our recent industry recognition, please.
Yeah, fantastic. So thank you, Fred, and delighted to be here, everybody. And so as Fred said, we're a new solution to an old problem, the old problem being power and battery management in wireless and IoT modules and devices. Delighted that even prior to having our product released, we're already winning awards, and there's more to come. We've already won Consumer Semiconductor of the Year for energy efficiency, Medical Semiconductor Product of the Year, and Product of the Year in power conservation, recognized throughout EMEA and APAC for these accolades, which we're delighted about. And I think what this tells us is that the product is easily understood. We're going to go into some depth today, but let's not forget that this is quite a simple new solution for the old problem. But there's more to come. I'm delighted that the product is recognized for being different, is for being category killing. And I think that gives an opportunity for everybody on this call to leverage some of those design features that we have. I'll also take the next one, if that's okay, Fred, as I wasn't sure we were going to do this last time. So we're also delighted to tell you that we're now a finalist in the Climate Tech Accelerator, which is run every year by Amazon. And basically, in a nutshell, what Amazon do is they look to the market and they invite green or energy efficient suppliers to apply to their Climate Tech Accelerator. And that isn't just electronics, it's the glue, it's the fabric on the back of the Kindle. They're looking for green alternatives for everything that they do. It's managed by a company called Plug and Play over in the Bay Area. And we've, for the last 6 months, it's something we've been dying to tell people about, but been unable to do so due to embargo. But we're a finalist. There's only 2 semiconductor suppliers that are actually in this far. There's ourselves and EPs. But effectively, we've had to demonstrate the ability of our nPZero technology to Amazon and prove to them what we say the product does, that it actually does, that it does reduce the power consumption of a battery powered device. What this means for us is, and we're partway through this process, is that we're working with them now to prove the concept across a number of their products. And once that happens, we're on the AVL for Amazon, and we've been working with them and their engineering teams around the world. For us in Europe, we don't see as many products as you do that side of the pond. So you guys will know how the ecosystem, how large that ecosystem is from a product perspective. And we're delighted to be able to now announce what I've just told you. And that's literally all I can tell you right now. So a very exciting time for us, very exciting time for NanoPower. And again, some validation around our technology and the benefits that we're bringing to both the consumer, the IoT, and the AI-driven industry. Back to you, Fred.
Sure. Earlier, I referenced our dev portal, and Torben will go through this in a little more detail, but this is free, available without registration, and we call it, essentially, it's a one-stop shop for developers and FAEs to find everything that they need. You'll find all of the device documentation, data sheets, as well as documentation for our dev kit and our stamp, which we will talk about briefly. There's software architecture tools, white papers, etc. So everything that an engineer needs to get started and to jumpstart their design. In addition, you'll see in the lower right, there's a technical support button. That is the button that you will select to contact Torben and his team with any technical support requirements. Anthony, you want to take this one, please? We may have lost Anthony, so
Perhaps I should be unmuted.
Oh,
Yeah.
okay.
No, I'm here. I'm here. I was on mute. My bad. So look, here's the product. We've all seen a semiconductor before, so don't expect to be lit or set on fire by looking at a semiconductor on the left. But we basically have two packages. We're talking today about the G1S, which is our nPZero architecture. And it comes in two packages. We have the QFN32, which you'll see is slightly bigger, and we also have our CSP, our chip scale version, which I'm pleased to say samples are available of our chip scale today. We've got a large interest from the wearable sector in how we can support them. So the CSP, the chip scale, is the package that's also available, as well as samples of the QFN today. We've got a wider distribution strategy, which we'll touch on a little bit later on. To support that design win, we are absolutely committed to make that design journey for any engineer across the world as simple as possible. And for that in mind, we have two dev kits. We have the bigger dev kit on the right, which I'll switch to straight away, which is a kind of a captive sandbox, where we have the nPZero on the left-hand side of the PCB. There's a number of power inputs, number of sensors you can fit on the right-hand side. There's a daughter board on there for your MCU. It comes complete with an STM32, and the nPZero is on the dev kit itself. What it allows you to do in engineering is to kind of play around with the parameters of the nPZero and use our configurator, which we'll talk about in a little while, to prove to yourself the benefits that using something like a power saving IC as a companion can give you. But if you really want to supercharge your design journey, I'm going to talk to you about the stamp, which is a central product here. It's literally a snap-in, snap-out module, which comes with some headers, which allows you to, through a breadboard, connect this to an existing design and just kind of turn it on and off. It's not as simple as that, of course, but that's the intention. With support from us, it allows you to get something like the stamp, look at an existing design that you may have problems with, and then use the stamp to be able to quick prove what the nPZero can do and supercharge your design to be ultra low power. Now, these three pictures, these three images, these are all available today, not in huge production quantities, but if you want a stamp, you want a dev kit, you want some samples, they're available today. We'll ship them to you this week. Fred, over to you.
All right, Torben, can you take the next 3 slides, please?
Yeah, sure. So I guess in the next slide, we're sort of trying to show what's the difference between a traditional IoT type system and a system where you're using the nPZero. And to look at that, we start by looking at the traditional system. And most IoT systems, or at least low power systems, they basically have the same components. You have some kind of power source, which could be a primary cell battery or a rechargeable battery or some kind of energy harvesting solution. Then you have what we call the host. And the host is essentially the main microcontroller of the system. And it's the host's responsibility to control the other parts of the system. In a traditional system, the host will have various peripherals connected to it. It will have to initialize these peripherals and read them at different intervals and do various processing and other tasks based on that. Normally in an IoT system, of course, there's a wireless aspect as well. So most of the applications we target, the MCU or the host will have some kind of wireless connectivity also. Then if we look at how this changes when you use the nPZero. What basically happens now is that instead of everything being connected directly to power and the host being in charge of the whole system, the nPZero now sort of slots in between the different components of the system. This means that the nPZero is the only device directly connected to power, and then we use power switches to switch on and off the different components only when they're actually in use. And again, we use this sub-threshold design. It means that our device can run at extremely low power levels compared to these other components. So for reference, when we are keeping track of time and sort of doing the scheduling in what we call idle mode, we only draw about 100 nanoamp, which is usually several orders of magnitude lower than what these other components can do in their sleep modes. And then what we can do, we don't only have the power switches, but we also have controls in our device to actually initialize and read sensors. So what we do is that we can wake them up at different intervals. We can initialize them based on the configuration memory in our device, and then we can read the value of the sensor. Then we have configurable sensor thresholds, which allow us to add some simple logic where we can say that, for instance, we only want to wake up the MCU if this sensor is within or outside a certain range. And as long as it's within that range and it's not sort of triggering the wake up, we just keep the whole system running at extremely low power level. And then once you see some change in the sensor or a certain timer times out, only then do we wake up the host, and the host can take some action and maybe send a signal over the radio or something like that. Out of the box, we support I2C or SPI for the sensors. And we can also support simple analog peripherals, which communicate or send an analog signal to our ADC. And it's possible to connect an external crystal if you want more accurate timekeeping. I think that's it for this slide. So this is a more technical view of the device. You can see the nPZero device in the middle again. You have the power source on the left and the different components on the right. We have the power switch, as I mentioned earlier. We have one big power switch for the host, which can natively support up to 10 milliamp. So this means that if the peak power of your MCU never goes above 10 milliamp, you can basically connect it directly to the nPZero device without any switch in between. But if you do need to use a bit more output power, you can basically configure our device in a sort of logic output state. And then we just control an external switch that will power the MCU. So if you're doing something wireless, like most wireless devices might go above 10 milliamp, then you need to use an external switch. Then for the sensors, we have 4 separate power switches for this. They go up to 1 milliamp natively, so low power sensors that only draw 1 milliamp, you can connect directly. And then the same thing, you can use a switch if you need to use a more high power sensor. Then we have a basic digital core in our device. So we don't have an MCU core inside. Instead, we have a sort of configurable state machine, which you configure by writing a set of configuration registers over the I2C interface. We also have a small clock timer module, which handles the base timing of the system. Here you can optionally connect an external crystal if you want more accurate timing. We have the ADC, which has one internal channel and one external channel. We have a small SRAM block, which we use to store initialization and configuration data for the sensors. The next slide.
So Anthony, can you speak to the some of these verticals, please?
I can. Thank you, Fred. Thank you, Torben. Yeah, I guess what's one of the most interesting features of the nPZero is the fact that we fit across a wide number of verticals and applications. So if you think about it, effectively anything with an MCU, anything with a battery or energy harvesting that is using sensors, is a pretty good candidate at the top of the funnel for anything that the nPZero can provide a benefit for. And as such, if you think of wireless modules, whether it's goods monitoring, smart buildings, ecology, consumer, medical, we fit across all of these verticals. In fact, the number of active designs we're working on actually exceeds this significantly. But the idea of this slide is really just to think about, there isn't really an application outside of of any of these that it doesn't fit as long as you have that MCU, energy harvesting or power. That kind of wireless module that's sensing somewhere, could be anywhere. It could be a heart rate monitor. It could be goods monitoring for goods to be traveling across the US. It could be agriculture to locate cattle where it's pinging on a regular basis, or you're looking for some kind of fall. It's all over the place. But I guess the main feature is that what we're doing here is we're making these applications far more efficient. We're taking that power budget and we're absolutely running it so efficiently that we're achieving 50 to 90% lower power consumption with a very similar design. Next one, Fred.
Sure. Torben, you want to take this one, please?
Yeah, sure. So this slide is showing one of our earlier demos. And this is a demo that we did in partnership with a company called TDK, which is working on a lot of solutions for energy harvesting systems. So they're basically making these kind of solid state battery cells, solar panels, and regulators, which sort of go into these energy harvesting products. And energy harvesting is maybe taking a while to sort of catch on. One reason of that is cost, I guess. It's sometimes hard to compete with dirt cheap coin cell batteries. Another part is that obviously energy harvesting is a bit unpredictable. You don't always know how much energy you have available. It might change. Like for solar, it will be high in the day and it will be very low at night. Other types of energy harvesting can come and go at different times. So it really means that you have very limited energy available and it can be sort of unpredictable. So what we did with this demo is that we put quite a lot of sensors on this board. I think we have 4 or 5 different sensors, including temperature, humidity, air pressure, IMU acceleration, and also time of flight for sort of movement detection. And we are able to run 4 of these sensors, reading every 4 or 5 seconds. And the total power budget for all the sensors is less than 1 microamp. It basically means we can read quite a lot of sensors and still be sort of in the nanoamp range, which is our, should we say, ultimate goal. And the graphs on the left just showing a comparison when we tested this system with the nPZero and without the nPZero. So the interrupt-driven case is basically whenever the sensors are doing the sort of sensor triggering internally and just triggering an interrupt when something is changed. The I2C-driven case means that we're actively polling the sensors over I2C. And in both cases, we see about 90% reduction in average system current.
And Anthony, you want to take this one, please?
Yeah, we just got a small example here of some of the range of applications that we've got design-ins with, and I think it's also worthwhile mentioning that there's a number of designs that we've been successful working with our customers with that could not exist without the nPZero. You know, for example, the wearable UV meter top left here, you know, it could not exist in this form without having the low power performance that the nPZero enables. I mean, that is not a feasible product at, you know, half an hour's worth of battery charge. We can take that to 63 hours. So it's a pretty simple device. I can run through some of these if you like, but it's effectively measuring UV intensity. And when we reach a threshold, it alerts the user through Bluetooth on their phone and all the data capture, etc. in there as well. But I think importantly for me, we're polling sensors on a regular basis here, turning off the MCU, and with that in efficiency, just waking up on a threshold, that's where you see that massive change there from battery consumption from half an hour to 63 hours. And that's something to consider, is that's enabled that product to be in existence. There's more that we've got that we can talk about, although they're under non-disclosure, very generally around some of these use cases. But again, if we think about the range of verticals that we showed on a couple of slides earlier, you know, we're into agriculture. You know, if you think about an agriculture sensor, it's generally in a field. It's difficult to get to. Changing batteries is expensive. You know, the human cost of changing batteries is significant. So anything that an application like that, where you can save that human cost and improve the efficiency of the device by enabling something like energy harvesting so it can stay on its own longer, makes a huge difference. And again, you can read the change here in performance from nearly 2,000 hours up to 6,500 hours almost. There's a big change there in terms of people getting out into a field and having a look at this particular product. And again, just in terms of the range, there's some consumery type products here. We've got presence sensors, and for the elderly, there's emergency wearables here. So, one of the challenges that we find in some of the B2C, the consumer product, is around consumers not charging devices, particularly the elderly. It's been found. The challenge that the customer had with this emergency button was that the end users, the customers themselves, just forgot to recharge. They put this around their neck or around their wrist and they weren't recharging it. So therefore, the effective use of a device like this was restricted. We've taken that up to nearly 5 years worth of battery charge by being able to turn off the MCU and let the nPZero as a companion manage that circuit, waiting for a threshold trigger, such as an accelerometer or heat, for example. So it's a good example of some of the breadth and width we've got. We could go on. I mean, there's wearables in here. There's fitness trackers that we're working with at this moment in time. There's temperature and humidity sensors in various forms in terms of IoT. I think the message here is we get the right use case here. The benefits are significant.
Excellent. Thank you, Anthony. So finally, the last slide before we turn it over to Torben. So during Torben's in-depth technical discussion and live demo, I'd like to ask you to consider your application where you think the nPZero may be the best fit. By all means, this is an interactive session, so ask questions. Feel free to interrupt the presenter or post them in the chat and ask the questions about your specific use cases. If there's something you'd really sensitive information, you'd rather not dive into a lot of detail, following this seminar, please contact your local rep at Selmark. We'd be happy to arrange a more in-depth customer-specific discussion to review your application and give you our feedback. So with that, I'm going to stop sharing and turn it over to Torben.
All right, can you see my screen, guys?
Yes.
Yes.
Perfect. Yeah, so again, just quickly back to the sort of comparison between a traditional IoT system and an nPZero based system, because this is a critical difference to sort of understand. So here again, we have a slightly different view. You have some kind of power source. You have the CPU, or what we call the host, and you have a number of different sensors or other peripherals connected to the system. And in a traditional system, everything is managed by the CPU, and it's sort of running everything from itself. And everything is also connected to power. Once the nPZero is added to the mix, we basically go in between the power source and the different components. And we also go in between the sensors and the CPU in terms of the configuration and data exchange with the sensors. And the first thing that happens when you power up a system with the nPZero is that the CPU is always enabled by default. And the reason for that is that we don't have any non-volatile memory in the nPZero to store the configuration. So it's basically the responsibility of the MCU to write the configuration of the nPZero the very first time you boot the system from a power reset. And that also means that when you boot up the system, the CPU will essentially be the master on I2C bus and will be able to send commands to the nPZero at will. Once that phase is over, the CPU can send a special command to the nPZero that instructs the nPZero to take over control of the system. When that happens, the CPU is completely disconnected to save power, and the nPZero starts running the sensors based on the configuration that the CPU just applied. And then it will read all of the sensors based on these different intervals, and it will configure the sensors and also read the value of the sensor that is used as a basis for this kind of threshold detection. And once a trigger happens, then it can sort of wake up the system, and the CPU can read the status of the nPZero and react accordingly. So this is another way to sort of look at the optimization introduced by using the nPZero. Here we have a traditional system. We're sort of seeing the current consumption over time going here. And a sort of easy simplification of an IoT system is to look at everything in terms of intervals. Basically, you're doing different activities at different intervals, depending on sort of the responsiveness need of the system. So typically the CPU will have some basic processing, RF, all the things that needs to be done at a certain rate. And then you have these different sensors that needs to be read at certain interval as well. And the current consumption of the MCU is basically this sort of passive processing, other tasks, and also the energy needed for the MCU to read all the different sensors. All of these devices have sleep currents as well. So the sleep current is also adding up to the total system current. And in these type of IoT systems, you can often see that the system spends 99% or more of time in sleep. So it means that the sleep current is really relevant for the overall current of the system. So the difference once you add the nPZero into the mix is that for one thing, you get rid of all the sleep currents because now the nPZero is essentially turning everything off when these devices are not in use. Also, you get rid of the MCU reading the sensors. So now it's nPZero reading all the sensors, and the MCU can be completely shut off at that time. And then you basically use our current for reading the sensor. And for comparison, when the nPZero is reading a sensor, the total active current of the nPZero is around 1 microamp. And most MCUs, for comparison, might draw hundreds of microamps or milliamps when they're actually reading a sensor. So then you get this sort of simplified formula here for the total system current. But there's no free lunch in engineering, so there's always a small trade-off. In our case, the trade-off is that you get a bit of boot energy, because when you're completely disconnecting power to the components in sleep, it means that they sort of cold starting every time. And that means that there is a bit of extra energy needed to sort of wake up the sensor. And it's fully possible to keep sensors on all the time if you want. So if you find a sensor that has a really good sleep current, but has a quite large boot energy, or you know that you're going to wake up often, you can decide to just keep it on all the time. So you can sort of make that trade-off between the sleep current or the boot energy. But the critical thing about the boot energy is that this charge here is above the interval in time. Basically, it means that if the time interval is small, this becomes a bigger impact. If you have a large time interval, this makes less of an impact. So the nPZero is really useful for systems where you don't need to run the CPU very often. You don't need to read sensors at kilohertz. It's more like seconds or minutes between readings. Then the advantage is much bigger. So this is what the graph is showing here. Typically, we approach close to 90% or even more than 90% savings if the interval is long. But then if the interval is really short, then the savings get sort of eaten up by this boot energy trade-off. This is another way to look at operation of an nPZero-based system. When you wake up of a power reset, it's basically the host MCU that is powered up, and the host MCU has the control of the bus. Then it's up to the host to write the configuration of the device. Once that is done, the host can then go into this idle mode. And this is this really low power 100 nanoamp mode where the nPZero is running the system, it's running the timer, it's having these different polling periods for different sensors. And whenever one of these polling periods expires, it will then go into this peripheral state, or polling state, as we call it. Here it will power up the power switch of the peripheral. It will initialize the peripheral, then there's a small delay, then it will read the peripheral and see if a wake-up trigger has occurred. If that's the case, it will turn the host back on, otherwise it will go back into this low power state. It also has an ADC trigger, which is running sort of in parallel. You can wake up on an analog signal. And you have something called a global timeout. And a global timeout basically means that barring any other wake-up sources, you will still wake up the system after a certain amount of time. So this is useful if you need to send some kind of keep alive message to the cloud, or you need to do some basic processing on MCU every so often. Now we're going to talk a bit about establishing the configuration of the nPZero. So we are not a programmable device. You can't write code for the nPZero. What you do is that you write configuration into a set of configuration registers. And to do that, we have this dedicated tool that can be used for the purpose. And this is essentially a desktop tool that allows you to visualize the configuration of the device and also generate these configuration sets. And what we've done here is we've basically taken all the configuration registers from the datasheet and broken it out into this sort of interactive desktop tool. So in order to write or read the register, you just use a 8-bit register address. This is very similar to how a lot of I2C-based sensors already work. Basically, every register has a unique address, and the first byte of every transaction is the address of the registers that you want to read or write. They all have a name, they all have a value, and they have different fields which control different functionalities. And here you can sort of mouse over any field, you get a description what that field means. You also get an overview of the different values that can be assigned to this field. And here you can also change the values interactively to sort of establish the configuration that you want to use. But this is quite technical presentation with all the bits and bytes sort of broken out. A lot of people don't have the inclination or interest for this. So we also have a more sort of high-level view of the configuration. And here the same functionality is available, but it's broken out into more high-level graphical elements. For things like time, like how often do you want to wake up the host, barring any other wake up, you can sort of set this directly in minutes or seconds instead of having to figure out how to do the conversion between register values and time. And then we have these 4 different peripherals that we support in the G1S device, which is the first device that we have. Once you enable one of these devices or peripherals, it basically opens up a separate configuration for that particular peripheral. All of these can be either I2C or SPI. There are some different modes that you can use in sort of setting how do you want to interact with these peripherals. The most common one is that you power it up periodically, you initialize it, then you read the data and you compare against the threshold. And then that can trigger a wake up. We also support sensors with interrupt pins. So you can power it up periodically, wait for an interrupt to happen, and then only after the interrupt happens, we read the data and we do the comparison. We also support basic asynchronous sensor that simply set the interrupt pin at any time. And that can also be a wake-up source of the device. A power switch can be either a power switch or a logic output, like mentioned before. We support some different data types and different options related to I2C and SPI communication. They all have an individual polling period, like mentioned before, individual data thresholds. And also you can configure a delay, which will be applied. There's one delay that's applied before initialization, and one delay that's applied before you read the value of the sensor. And there's also some sort of utility functions here that allow you to benchmark the energy consumption of the sensor. So I can see if I have some preset sensors that I can demonstrate this. So there are some sensors that we have tested in-house that we provide presets for. So in case you want to use one of these sensors, it's really easy to load the preset. And then we immediately show how to configure the nPZero for that particular sensor. Let's see. For some of these sensors, we also done the benchmarking of the boot energy and the poll energy and the sleep current. And what that allows us to do is you can basically calculate the relative savings when using nPZero based on the polling interval. So you can sort of set this polling interval and then you can see what kind of savings you get based on this particular sensor. But then the last part of the configurator is that we also generate a code snippet. So this code snippet essentially integrates with the nPZero driver API. And this is a basic C library that can be ported to different MCU families. And it basically allows you to configure the nPZero by configuring this sort of configuration struct here. And all the configuration you do in these 2 views will also be synchronized with a code snippet. It will basically just populate different structures. Each peripheral gets a separate struct. The ADC gets some structs, and then you have a global struct that sort of compiles all this information into a single struct that you can then later on refer to in the API. Down here, we're basically running the main file of this example, initializing the nPZero driver, reading status registers of the nPZero, and then configuring the device based on this struct what we looked at before. Then once you're done with all the initialization work, you call this go to idle function. And that basically means that the nPZero will take over control of the system based on this configuration. And then once you're happy with the configuration, you can save this file. And then you essentially have to compile this as part of your MCU firmware. So again, the code doesn't go into our device. The code goes into the host MCU.
Torben, there was a question
So
in
the-
the chat. They
Yeah.
said, is there a debounce option for wake signals?
No, I don't think we have a debounce, no. Other than, I mean, it's being polled at a relatively slow rate, so there'll be some natural debouncing there, but there's no special debounce function, no. And then, for the time being, we support STM and nRF52, so Nordic nRF52 series. So we have these supported, but we also have a very basic register map configuration, which just gives you a basic array that you can easily write over the I2C interface to configure the nPZero. So if you want to support an MCU family that we don't natively support, then it's quite easy to use this register map function. Once you're happy with the configuration, you can save XML file with all these configuration details, which you can then put as part of your code firmware repository or anything else you want to do. I think that's it for the configurator. Any more technical questions before I proceed to the demo?
Nope.
No? Yeah, sorry. So for the demo today, basically going to look at sort of a home automation example. So this is just a screenshot from my own home. I'm running this Home Assistant, which is a sort of open source home automation platform. And what you always end up doing when you start with home automation is that you run out and buy a lot of cheap temperature humidity sensors. In this case, I found a 10-pack of sensors on AliExpress, basically to fill every room in the house with a temperature humidity sensor. Once you have that in a system like this, you can start to connect it to all kinds of automations and statistics and whatever else you want to do. But the problem here, of course, is that each of these sensors runs out of battery after about a year. And once you have 10 of these sensors running, then you're basically running around replacing one of these batteries every month. And that adds up quickly. It's a lot of waste, some cost, and also a lot of work. And obviously, if you're running a commercial installation or some kind of industrial application where you suddenly have thousands of sensors, this is a big problem. So I basically wanted to see, can I recreate this kind of basic temperature humidity sensor with the nPZero? And what kind of performance can I achieve in that case? So what I did was to make a small PCB, which is this nano stacker. Basically what it has is a Nordic Semiconductor nRF54L15, which is a good low power short range radio, which can do Bluetooth and Zigbee and other short range protocols. It has our nPZero G1S, and it has a Texas Instruments HTC 2080 temperature humidity sensor. And here we can see this board running connected to a joule scope. So a joule scope is a tool that we use a lot in the lab because it allows you to measure current down to a nanoamp level with very high degree of accuracy. And we made a small script to essentially visualize the current from the joule scope in a slightly more intuitive way. So this is showing this system running. Here you can see the idle current is around 100 nanoamp, which I mentioned before. It's reading a temperature sensor every 8 seconds, which is, temperature doesn't change that often. This should be more than fast enough. And you can see when it's only reading the sensor, the total average current is around 200 to 250 nanoamp. And it might be hard to see, but I tried to visualize the expected battery lifetime on the CR2032 coin cell in the middle here. So if you were only reading the sensor, in theory, you should get about 100 years battery life, which of course you would never get in real life, but it's still showing something about the base current of this kind of system. But of course, we need to do more than that. We need to send a signal to the world, otherwise we're not going to have any IoT product. So once every minute, even if nothing happens, it will wake up the Nordic device and send a signal over the radio. And what you can see with one wake up every minute, you're still looking at only about 2.1 microamp in average. So yeah, it goes from a century to a decade, but still, for a system that sends a Bluetooth signal at this kind of rate, this is a really low number. And if I try to do this with a Nordic device alone, I think even the lowest current would probably be higher than this. So the total system is running at a very low power level. And then, of course, I have to see if this actually works in practice. So here you can see the blue line in the graph is the nanostacker with nPZero, and the yellow line is the reference in this case, which is this AliExpress sensor. And there is some offset, so maybe there is some calibration issue with the sensor, but you can see the trend is more or less identical. So at least in this use case, there is absolutely no performance degradation from sort of achieving a 10-time reduction in power. I think that's it for the demo. We still have 14 minutes for Q&A.
Thank you,
Thanks,
Torben.
Torben.
Thank you.
Yeah, thanks, Torben. So I think just if we just review a little bit what we've gone through there, we got the power saving IC, which is a companion chip to the MCU that allows you to autonomously manage sensors without the MCU being in operation, which then gives us that huge benefit to the power budget and battery life. Just talking around what we've got here, again, just talking about applications from both customers and personally what we've got there. Any feedback from the team? Anybody got any questions on how we do this? What use cases?
Yeah, but Anthony or Torben, well, you have covered a lot of, or you demonstrated that several different applications. Maybe not so much for Jerry in this instance, which is a wearable medical device, but what's the ideal application for us where you're gonna get the most power savings? What are the
Yeah,
right
so I can-
conditions where you're gonna get that
Okay.
90%?
Yeah, I can take a crack at that. So especially sort of what we call event-based products, where you're sort of waiting for something to happen. So you're not constantly streaming data, but something like temperature, where most of the time it's very stable, but then maybe suddenly someone opens a window or a fire starts, and you want to be able to quickly respond to that rapid change in temperature. So, or these kind of logistics products, if someone drops a package, you want to log it, but you know that most of the time someone is not going to drop a packet. So it's a lot of these applications where either something is happening at a very slow rate or it's happening intermittently. So most of the time you're just checking the sensors. Is anything happening? Is everything okay? You don't have to run the radio. You don't have to run a lot of MCU. But then once something happens, you want to respond to it quickly. I think those are sort of the strongest fit for us, because then you can achieve a greater amount of savings.
Yeah, I think it's a great question, Jeff. I think it's easy to think about sometimes I think about what's not a great use case, because it's kind of quite wide, and not a great use case would be something where you need to be polling the sensors that often. That isn't feasible to turn off the MCU. That's not a great use case. I think when we talk about temperature and humidity, because they don't change very quickly, very often, allows you to have a decent polling time between these. And actually, part of the configurator is how you can tune and extend those and kind of model it with the battery usage to optimize the system as well. I mean, I think for me, the simplest one for me is goods monitoring temperature and humidity in a container. We know from customers we've spoken to that the MCU can be often 95% of the time in an application like that versus being on. So the impact in terms of performance is huge. So that's probably one of the most extreme examples we've got. And kind of, you've then got devices which are waking up some kind of LoRa or communication protocol which has got either a long startup or a big current draw, which no matter what we say with the nPZero kind of obliterates it. So it kind of sits somewhere in between, if that makes sense. But yeah, rule of thumb, you can turn the MCU off, We can poll sensors on its behalf, and we won't wake up the MCU until it's absolutely needed. We need to record something or trigger some response to a threshold being hit. That's the perfect application for us, and it's just across all those applications. Yeah.
Yeah. Torben, I've got a question, right? So let's
Brent?
talk about.
Sorry.
Yeah, I was just
I'll
going to ask
only-
about.
I'll
Hold
only
on.
interrupt you because I think Jerry's mic has gone off a couple of times and he may have a question. I want to make sure we get him in.
Okay.
Come on, Jeff. Let's get Jerry. Let's get
Well, so thanks for the great presentation. You guys are answering most of my questions along the way, which was great. The ADC, I don't know if you mentioned how many channels, the sample rate, how many bits.
Yeah, so in the G1S, which is the product we have today, it's only one channel. So it's essentially an internal channel connected to the supply of the nPZero and one external channel that you connect to something else. But this one, it's very low resolution. It's a 6-bit ADC, and it's running at the maximum of 1,000 hertz, or about 1 kilohertz. So
Okay.
it's really only for, like, coarse measurement of maybe you're charging some kind of storage element or something like that. But I don't know, Anthony, if you're okay to talk a bit about the next iteration. So we are looking into improving the ADC. Yeah. So in the next chip coming out later this year, I guess, we will add an extra channel, and we'll also increase it to 8-bit resolution. So it will be a bit more usable in the next chip for sure. So that will be 2 external channels, 1 internal channels, and yeah, 8-bit.
Cool, thanks. And the number of digital I/O on this chip?
Well, call it digital I/O. So we have 4 power switches for the peripherals, and you have 4 interrupt pins, and you have 4 chip select pins. So that's sort of the digital I/O. So you don't have, GPIO in that sense. So the power switches work a certain way, the interrupt pins work a certain way, and the chip select are only for SPI. But it's worth mentioning that the interrupt pins can actually be used as outputs. So it's possible to configure the interrupt pin to flip when you have a sensor or like a trigger wake up. So you can basically set up a sensor to sort of flip a pin every time it goes outside or inside that range that you have configured. So yeah, you have some extra flexibility there.
Cool, thanks. And another random question. Could you drive a piezo with an H-bridge using 2 signals? So let's say a 3 kilohertz tone, one side high, one side low. Is that possible?
Yeah, well, not really. I mean, in the G1S, we have this kind of clock output, so we can generate a basic 32 kilohertz clock, which can go down to 1 kilohertz, I guess. You can sort of divide it down. So I guess you can do something in the audible range if you want. But it's only one output, so if you need inverted signal, I guess you need to fix that in some other way. So for sort of PWM type things, it's not very good for that. We don't really have a proper PWM module or anything like that.
Okay.
Jerry, is that because the needle is piezo driven? Is that why you're asking?
No, it's our alarm, essentially. So we have an ASIC that does a lot of these functions. So I was envisioning this chip as replacing that ASIC with more flexibility. And these are some of the functions we do today as backup safety to our SoC BLE chip.
Interesting.
Makes sense, yeah. I think just talking about the product we're going to be launching towards the end of the year, it's really a build on what we've got. It's we're finding a lot of customers now are working on the nPZero and then transitioning through, because the pinouts are very, very, in fact, the same pinouts. The configurators is the same. It's a transitionary thing. So we're getting a lot of development work being done now in anticipation of some of that. So I guess it's just a question of getting product in people's hands and getting to play with it. So any questions from you, James? Sorry, I'm picking on you, James, only because I noticed you're from Candela Medical, and we're always interested to talk to our customers and get feedback.
Yeah, at the moment, I'm just absorbing what you're putting out there.
Yeah.
I don't know where I would use a lot of the power management right at the moment. it's something to look at for our future, and I just want to see what's available from you. I noticed the
Yeah,
medical
and this-
devices that you're incorporating it into, the sensors and stuff like that. We do a lot of that, and the polling. Security, I'd be interested in that. Are there, we're getting asked, or it's in the specifications for more secure devices. So
yeah.
I have to look a little more into it, but I'm just, like I said, curious at looking what you're offering and seeing where it's at.
No, that's a good point. I guess, one of the points of having the webinar is because this is a unique take on that old problem, new solution to an old problem. It's interesting to think about where this could go, rather than being so we're getting a lot of systems that are being built around this, rather than being just a slot in, which is what it's also designed for as well. So we're happy to help you with any questions you've got, James.
All right, yeah, like I say, for our legacy items, the devices we have today, I don't see a lot of plus side for us, but going into the future, where we're transitioning to devices versus just lasers, how could this be used for us? So interesting to look at.
Yeah, great stuff. Interesting to hear. Thank you.
Yes.
When we've
Hey, any more
we've
questions?
kind of- No, sorry, Anthony. I know we've coined this as a PSIC, which is not a term we've heard yet, instead of a PMIC, but the general difference, or what's the identifier, the main difference why we're calling this a PSIC over a PMIC?
Yeah,
Yeah,
so
go ahead,
should I
Toby.
take that one? Yeah, so we're basically optimized for low power sensor systems. And we will switch on and off the MCU and the sensors. So in that sense, it might be a bit like a PMIC. But our main functionality, is being able to switch them on and off on this schedule, being able to initialize sensors, read, do all this kind of automated work in the state machine. And that's not something a PMIC is doing. And then inversely, what we don't do, which a PMIC might do, is, regulating power and handling charging of batteries and these kind of things. So we don't really concern ourselves with that. That's what typically you would have a PMIC do. So, if you have unregulated power outside the voltage range, you will need to have a regulator separately. We don't handle that. So, you might see applications where a PMIC and a PSIC actually could work together, where that would make sense. So we're more complementary than replacing a PMIC.
Thanks.
Yeah, exactly.
Yeah, I think it's more of we're more of a companion IC to an MCU that allows, the kind of the way that it works. We want to try and differentiate ourselves. I mean, it's part of our distribution strategy is to be with, DigiKey and Mouser, and we've already got agreements. We're just waiting for stock to be in with those guys. One of the challenges we found was this is kind of a new category of product. It's not a PMIC. If you think about the hierarchy within the catalog guys, where do you sit with a product like this? Well, we know it's in power management, but does it sit underneath PMIX? No. Does it sit with a low power MCU? No. It kind of sits somewhere in between. So we're coining the phrase PSIC. It's but we're if you want to be really, we're autonomously controlling sensors on behalf of an MCU, and we're enabling the MCU to be turned off while we do so, and then use that power efficiently. I mean, if you think about an MCU and the power draw it's got just to be polling a temperature sensor, it's like great British phrase, sledgehammer to crack a walnut. It's a lot of power being used in your circuit for nothing. And there's applications out there where this golden barrier that our CEO always talks about, 1 micro for an MCU, just can't be broken. Nobody's been able to crack it. You stick a companion chip, PSIC, and all of a sudden, we're asleep at 90 nano, and operating at 200 nano. It's groundbreaking when you look at it in that way. Find the right application, all of a sudden, we've changed the game completely.
Sense.
So we're right
Cool.
up at
So-
11 o'clock. Really appreciate everyone's participation. Like you said, if you think of some questions after the fact, please contact your partner at Selmark. We'll be happy to discuss any questions. Use the technical support button on our dev portal if you like. Or if you have an application you'd like to go into a little more depth in, we're happy to set up a specific call with individual customers to review that. So really appreciate everyone's time here, participation, active discussion, and certainly look forward to continuing these discussions with you directly.
All right,
Thank
thank
you.
you.
Appreciate
Thank you,
your time,
Nanopower
Thanks
team.
so
everybody.
much, guys.
Jim,
Thanks for
thanks
joining,
for
Gary.
joining.
Thank you.
Bye.
Bye-bye.
All right, bye.